Transportation engineers tend to talk about the interstate construction days with just a touch of nostalgia, and with good reason. There were some huge construction projects, work that called on the very best engineering talents available. The challenges were tremendous. Roadways, ramps, bridges, drainage structures, all in one integrated system. The scale of the interstate network is truly awesome. In comparison, you tend to think of today's projects, largely reconstruction and rehabilitation, as being far less challenging. Right, except for that one little variation: traffic. The interstate system was constructed on new right-of-way, and most of it was done with no interference from traffic. No wonder there's nostalgia in the air. Virtually all of today's highway work is done adjacent to or in the middle of traffic, and high-speed traffic at that. Today's construction or maintenance worker spends the whole day trespassing on the driver's territory, and that driver doesn't want to give up 1 inch of the roadway. Doesn't want to slow down either. Getting that driver through a work zone safely is a challenge that matches a lot of those that we faced in the interstate days. Fortunately, as a result of research and development over the past decades, we have some impressive tools to work with: standard signs, cones, drums, barricades, and the rest. If they're applied with good, solid engineering judgment, following the standards in the MUTCD, the margin of safety is greatly enhanced. This program focuses on just one traffic control device, and it's a powerful one: the Advance Warning Arrow Panel, commonly called Flashing Arrow Panel. Advance Warning Arrow Panels are sign panels with a matrix of lights capable of either flashing or sequential displays. In places where the driver's attention might be divided a dozen ways, the Advance Warning or Flashing Arrow Panel is riveting. The driver's eye goes straight to it, and the message is clear. Even at night or in bad weather, when visibility, perhaps more than any other factor, determines whether the driver is going to make it to the other end of the work zone. The arrow panel's single outstanding message is lane closed ahead. It can be a one-lane closure on the right, the left, or in the center of a multi-lane roadway. Panels can also lead drivers through multiple lane closures, left, right, or center. Lanes are frequently closed by slow-moving maintenance operations, such as this striping crew. Arrow panels mounted on each vehicle in the convoy force drivers to pay close attention to the potential hazard ahead. And shoulder closures often call for advance warning as well, operating the arrow panel in its caution mode. Although the arrow panel is a highly useful device that carries a strong message and provides good guidance, it's not intended to be used alone. It's almost always used to supplement other devices. This program does not deal with all the other devices in the work area. For more information, refer to the Federal Highway Administration's Manual on Uniform Traffic Control Devices, the MUTCD, and your own agency's references. The federal MUTCD has explicit minimum standards for arrow panels. All state traffic control manuals must either conform with the MUTCD standards or exceed them. This program is designed to help out. It covers the mode selections, design standards, applications and placement standards, costs and equipment maintenance, and some general recommendations for operation and usage. First, of course, the mode selections. Arrow panels should have the capability of the following operating modes or displays: left flashing arrow, right flashing arrow, left sequential arrow, right sequential arrow, left sequential chevron, right sequential chevron, double flashing arrows, and caution. The caution mode consists of 4 or more lamps arranged in a pattern that does not indicate a direction. That's usually either 4 lamps in the corners or the arrow shaft alone. Now, many engineers prefer not to use just the arrow shaft, though, believing that drivers may interpret it as a malfunctioning arrow and may change lanes unnecessarily. If you have any doubt, use the 4-corner mode. To move traffic to the left or to the right, drivers appear to get the message most clearly through the flashing arrow and the sequential chevron. Those are the preferred displays for left and right side lane closures. So those are the standard mode selections: sequential or flashing arrows, sequential chevrons, double arrows, and the caution mode. Which brings us to the design standards. All arrow panels that conform to the MUTCD's requirements are rectangular with yellow lamps and a flat black finish for good contrast. To reduce glare from sunlight, the lamps have to be either recessed into the panel or equipped with hoods that cover at least 180 degrees. This design makes the display highly visible, even in bright sunlight or with distractions in the background. There are 3 sizes corresponding with 3 levels of traffic volumes and speeds. Type A panels measure 24 inches by 48 inches. They have at least 12 lamps and must be legible from a distance of 1/2 mile. They're appropriate for low-speed urban streets. Type B panels are 30 by 60 with at least 13 lamps, and they have to be legible from 3/4 of a mile. They're designed for intermediate speed and for maintenance or moving operations on high-speed roadways. And Type C panels are 48 by 96 with at least 15 lamps, legible from a full mile. Type C is designed for high-speed, high-volume roadways. All of these numbers are in the MUTCD, of course, along with the other requirements. There's no need to try to remember all the specifics. The minimum lamp on time is 50% for flashing arrows and 25% for sequential chevrons. Those minimums give you the best recognition factor. Both types of arrow panels must be capable of at least 50% dimming from their rated lamp voltage. The panel in this footage is being operated at full power, and as you can see, it's overpowering. As you get closer, it can almost blind you. Clearly, that doesn't add to driver safety. In contrast, here's a panel being operated at 50% of its rated voltage. Good recognition, high visibility, and no blinding glare. So the reasoning behind the dimming requirement is obvious. Although some panels have manual dimming controls, clearly it's best to have the dimmer operated by a photocell. Photocell systems operate automatically, sensing the ambient light and dimming the lamps appropriately. That way, no one can forget to turn down the brightness at the end of the day. Now, mounting height. The minimum height for all arrow panels is 7 feet, measured from the edge of the roadway to the bottom of the panel. Now, the reasoning here is obvious as well. Maximum visibility, even over vehicles driving ahead of you. There's one exception to the 7-foot minimum mounting height. It's not always possible to get the panel mounted 7 feet up on the back of a work vehicle. For maximum visibility and maximum safety, though, it should be as high as possible. As you'd imagine, the alignment of the panel head, both vertical and horizontal, has a direct effect on visibility. After all, if you can't see it, you can't respond to it. The horizontal alignment is controlled by positioning the trailer, and the vertical alignment is controlled at the panel mount. The goal, of course, is to make the panel visible from as far away as possible and to keep it visible as drivers approach the work area. Because of the panel's high-intensity lights, this isn't a precision alignment, but the operator should always be trying for maximum effectiveness. The power supplies of aero panels include diesel, gasoline, solar, and batteries. While the MUTCD does not contain any standards for power supplies, some state transportation agencies require self-contained power supplies that are capable of running aero panels for at least 72 hours. Diesel generators are the most commonly used power supply, and while some gasoline-powered generators are still operated, their use should be avoided whenever possible. Because aero panels are often exposed to traffic, collisions are possible, and, in an accident, diesel fuel presents a lesser fire hazard than gasoline. The use of solar-powered aero panels is becoming more widespread. Solar collectors mounted on the trailer charge batteries that power the lamps. The collection panel should be positioned to catch the maximum amount of sunlight. And there should be enough batteries to power the lamps during periods when little sunlight can be collected. Fully charged batteries can run a panel for weeks, depending on ambient temperature. Other aero panels are powered by batteries alone. As the batteries are used up, they are rotated with recharged ones to maintain a steady power supply. Of course, vehicle-mounted panels don't require their own power supply. They're designed to run off the vehicle's battery system. Okay, so those are the design standards. Now, applications and placement. Situations best suited to the use of an aero panel and where to place it for best results. As I mentioned earlier, the aero panel's overriding message to drivers is lane closed ahead. Research has shown that drivers start preparing to merge as soon as they see an aero panel. Lane closures, then, are the single most suitable application. But not to close one lane of a two-lane, two-way road. Clearly, if you close one lane of a two-way road by using a flashing arrow, drivers could be guided into the path of oncoming traffic. Aero panels are primarily suited for use on multiple lane roadways. When an aero panel is used in conjunction with channelizing devices, it's always best to install the panel off the roadway at the beginning of the taper, on the shoulder if possible. Now, granted, the panel isn't directly in line with the driver's eye, but the message is still clear. And you have to remember that the panel itself is a potential collision hazard, so it's best to keep it out of the way. For a single lane closure, a transition taper of length L is formed with channelizing devices. L is determined by using one of two formulas given in the MUTCD. This is followed by a buffer space of sufficient length to give the driver one last opportunity to bring his vehicle to a stop before entering the work area itself. The buffer space and the work area are outlined with a series of channelizing devices. And finally, the aero panel is placed in its standard position at the beginning of the transition taper. In a multiple lane closure, most transportation agencies run the standard taper length L to close one lane, then a tangent section of 2L to allow traffic to stabilize, then another taper L to close the next lane, and a tangent section running past the work area. An aero panel is placed on the shoulder at the beginning of the first taper, and a second panel is placed in the lane that was closed first, at the beginning of the second taper. For the center lane work area shown here, first the left lane of the roadway is closed. An aero panel is placed on the shoulder at the beginning of the lane closure taper. A standard taper length is set up, followed by a tangent section of 1/2 L. Then the traffic is divided, allowing the right lane of traffic to pass to the right of the work area and the left lane of traffic to pass to the left of the work area. The center lane is closed with channelizing devices as shown. An optional panel displaying a double arrow can be placed toward the back of the taper. That way the trailer fits well between the rows of channelizing devices and the panel itself doesn't encroach on the travel lanes. Frequently, space is simply too limited to put the panel off to the side of the closed lane where it should be. Here, for example, moving the panel to the right would place it on the sidewalk among the trees. So as the next best placement, it's been positioned as close as possible to the beginning of the taper, behind the channelizing devices. Placement at the start of the taper is always preferred over placement in the middle of the taper. So that's the general rule, either on the shoulder at the beginning of the taper or behind the channelizing devices, as close as possible to the beginning of the taper. But the real world isn't so neatly defined as that. No two work sites are identical, and the overriding rule is visibility. If drivers won't have enough time to see the panel and react to its message, make adjustments. Here's a quote from the MUTCD. Placement of the aero panel should be varied as needed to achieve recognition distances. So if hills, curves, or other obstructions reduce that desired recognition distance, the panel can be moved upstream by as much as 2,500 feet. If the panel must be moved upstream, try to locate it on the shoulder, not in a traveled lane. If there's no space on the shoulder at that point, you should probably consider bringing the taper upstream as well and extending the lane closure. Another problem to watch for is the potential for confusion with nearby ramps, median crossovers, and intersections. Take a close look at all the possibilities. How will drivers react to any single placement? Are you giving them the positive guidance they really need? Would a minor adjustment produce the effect you want? Lanes are frequently closed by mobile construction or maintenance operations, pavement recycling, patching, and so on. The aero panel mounted on a vehicle at the back of the operation uses the same panel displays as would be used for a stationary operation. A flashing right arrow for left lane closures, a flashing left arrow for right lane closures, and a double arrow for center lane closures. When aero panels are used for shoulder closures, they should be operated in the caution mode, not as a flashing arrow. The flashing arrow tells the driver to move over, and shoulder closures don't call for a reaction, just for heightened attention. So, those are the major applications and placement standards for single lane closures, multiple lane closures, center lane work areas, and shoulder closures. Now, some agencies use aero panels for another application, traffic diversions or shifts. But since an aero panel is mostly understood as indicating a lane closure, it should be used in a lane shift situation only after an engineering study justifies its use. Now, costs and maintenance. As you'd expect with a fairly complex piece of equipment, aero panels don't come cheap. Truck-mounted panels, depending on their size, cost something like $750 to $2,000. And you have to remember, they run off the truck's generator, so they don't have a special power supply. Trailer-mounted aero panels with generators cost about $5,000. Most engineers tend to agree that given the increased effectiveness in terms of traffic control and traffic safety, $5,000 is a bargain. But bargain or no bargain, $5,000 is an investment, and that investment has to be protected through regular scheduled maintenance. Like any other traffic control device, especially in work zones, aero panels need attention periodically. Of course, all engines need oil changes and so on, and the generator for an aero panel is no different. But in this program, we're concerned only with the maintenance work that affects the operating effectiveness of the aero itself. That is, maintenance that affects traffic safety. First, naturally, that means the lamps and lenses. The traffic control supervisor should frequently check the display to see that all lamps are lit. Replacing lamps may appear to be an unproductive chore, but an incomplete aero is an incomplete message to the driver. Given the time and cost invested in installing an aero panel, there's just no reason to settle for less than 100% effectiveness. Road grime is a concern in all work areas, and depending on the road conditions, the aero panel's effectiveness can be reduced by 50% or more in a short period of time. Lenses should be cleaned on a regular schedule, and the cleaning should be more frequent if road conditions indicate a reduction in visibility. As I mentioned earlier, many aero panels are equipped with photocells to automatically dim the lamps at night. You have to remember that photocells aren't fail-safe. They should be checked on the same schedule as the other maintenance items. If the sensing element is caked with road grime, the dimming can be actuated during daylight hours. And of course, if it's defective, it should be repaired or replaced. The amount of dimming required can vary a good deal from one location to the next. As you'd imagine, the ambient light in a brightly lit urban area is quite different from the light on a remote rural highway. The best test is a nighttime drive through the work zone, the first night the panel is installed, with adjustments made on the spot. The flashing frequency rarely needs adjustment. Just check now and then to see that the display runs at 25 to 40 flashes per minute. For most projects, one person should be in charge of maintaining the aero panels. On panels that have their own generators, very little is likely to go wrong between refuelings. But every time the tank is filled, the operator should give the whole unit a good look. Lamps, lenses, dimming controls, and so on. Panels without generators should be checked at least every few days. Same items. And in any case, all project personnel should be encouraged to watch for problems and report them as soon as possible. Like all other traffic control devices, an aero panel can be highly effective or practically worthless. Well, now that we've covered mode selections, design standards, applications and placement standards, and costs and maintenance, here are the key recommendations. First, make sure that all MUTCD standards are satisfied as a minimum. Then refer to your own agency standards. Don't use aero panels to close lanes on two-lane, two-way roadways. The potential for misguiding traffic is just too great. Whenever it's possible, place aero panels on the shoulder at the beginning of the taper. If there's no shoulder or not enough space off the roadway, place the aero panel as close as possible to the beginning of the taper, behind the channelizing devices. Where sight distance is limited, consider using a supplemental aero in advance of the work zone, or extend the lane closure upstream to a point where visibility is acceptable. If multiple panels are being installed, the spacing between them should be at least 3 times the taper length L found in the MUTCD, and never less than 1,000 feet. Closer spacings tend to overpower drivers, and they can react erratically. If a double aero seems warranted, watch the traffic movements immediately after installation. If it causes confusion, make adjustments or remove it. And finally, enforce all requirements for dimming the lamps at night. Drivers who are blinded as they pass an aero panel simply can't be expected to react safely. Aero panels are relatively new traffic control devices. The research and development efforts are far from complete. Given our relatively short experience with them, we basically know just 2 things. In the right situation, the expense really is a bargain. And in the wrong situation, or if they're not placed and operated with care, they can cause more problems than they solve. The flashing aero panel. It's a powerful device, not to be taken lightly. You see them in just about every work zone along our roads and highways. Officially, they're concrete safety-shaped barriers, or CSSBs. They've become an accepted traffic control device used by most state highway agencies and by more and more city and county agencies as well. Protection is the main function of barriers, the protection of motorists, pedestrians, and workers alike. While barriers may not reduce the frequency of accidents, they have reduced the severity of accidents involving construction activities that intrude into the traveled way, or involving motorists who intrude into work areas. Barriers may also be used to separate two-way traffic. And they may serve an additional function of channelizing traffic. However, this use should be determined by an engineering analysis of the protective requirements of the location, not the channelizing needs. But regardless of their usefulness, there is a problem with barriers. They're often hard to see. Despite their massive size, they tend to blend with the pavement and with their surroundings. This is especially true when the conditions and surroundings provide little contrast, or when rain, snow, dust, or fog hamper visibility. At night, it gets even worse. Concrete barriers can become a visual black hole. Most states, to increase barrier nighttime visibility, enhance barriers with a variety of channelizing and delineating devices. These devices mark the roadway's alignment and outline the course that vehicles must follow. Channelizing and delineating devices give drivers a line of discrete visual cues to guide them along a well-defined path through the work zone. This video program's aim is to improve roadway delineation practices at concrete barriers, principally at portable and quick-move barriers in construction and maintenance work zones. We'll look at the current standards for roadway delineation at barriers, two typical situations in which barriers are placed, some recommended delineation techniques, end treatment delineation, maintenance considerations, and finally, the factors that must be considered in the selection of delineation devices. So first, the standards. The existing national standards are found in the Federal Highway Administration's Manual on Uniform Traffic Control Devices, the MUTCD. Many state agencies have developed their own standards in addition, but in all cases, the state traffic control manuals must either substantially conform with the MUTCD minimum standards or exceed them. You should know your agency's requirements and follow them. As for the national standards, in Part 6 of the MUTCD, you'll find a definition and description of portable barriers. You'll also find references to the functions of barriers as protective devices, separators of two-way traffic, and channelizers. As protective devices, barriers are designed to keep vehicles from penetrating into areas behind them, to both minimize damage to impacting vehicles and their occupants, and to reduce the risk of injuries to pedestrians and workers. Barriers may also be used as separators of two-way traffic to reduce the potential for head-on collisions. In addition, barriers may serve as channelizers of traffic. However, the MUTCD points out that their use in this function should be based on an engineering analysis of the protective requirements of the location, not on the channelizing needs. When barriers are used as channelizing devices, they should have a light color for increased visibility. For nighttime use, the MUTCD requires that barriers be supplemented by the use of standard delineation or channelization markings or devices. Specifically, channelization markings are pavement edge lines, or lines supplemented with raised pavement markers, or lines simulated by closely spaced raised pavement markers. Channelization devices include tubes, cones, vertical panels, drums, barricades, and yellow warning lights. For nighttime use, the devices should have higher performance type retroreflective materials on them. Yellow warning lights may be installed to delineate concrete barriers. The first two may be Type A flashing lights, but all the rest must be Type C steady burn lights. The mounting height of warning lights should be about 38 to 40 inches, about the same height as when mounted on top of drums or barricades. The ends of barriers should be marked with object markers and treated in a crash-worthy manner to lessen the effects of impact in case vehicles hit them. Part 6 of the MUTCD also addresses roadside delineation. The retroreflective elements for delineating devices must have a minimum dimension of approximately 3 inches and should be about 4 feet above the near roadway edge. The standard color for devices used along the right side of roads must be white, while along the left side, the color must be yellow. In addition, Part 6 of the MUTCD addresses the minimum design and application standards for channelizing devices. Now, these devices vary in shape and size, but are always orange and white. Part 6 also addresses the design and application standards for warning lights. Now, that's pretty much it for the national standards. In the rest of this program, we're going to look at current practice and other recommendations and guidelines for roadway delineation to supplement portable barriers and improve their visibility. There are two main situations in which barriers are placed on the roadway, and these situations determine the devices to be used with them. Situation 1 is illustrated here, where traffic must be restricted to the travel lanes and where there's enough room between the barrier and the nearest open travel lane to place and maintain channelizing devices, then standard channelizing devices should be used. The MUTCD defines these channelizing devices as barricades, drums, vertical panels, cones, or tubular markers. So place and maintain channelizing devices wherever there's enough room, but do not place delineating devices on the barrier segments. To repeat, no devices on the barriers. The barriers still serve as protective devices, of course, but the channelizing devices define the travel path. In all cases, you also want to have a good edge line, one that's highly visible and of the proper color. The edge line may be a continuous line or a line supplemented by raised pavement markers, or a series of closely spaced pavement markers that simulate a line. Again, this is situation 1. Now, situation 2 is shown here, where there is little or no space between the barrier and the adjacent travel lane to place channelizing devices. The delineation or channelization can be made part of the barrier itself. Now, this is by far the more common of the two situations. Again, standard delineation calls for a good edge line, supplemented perhaps by raised pavement markers, and it calls for channelizing or delineating devices on the barrier segments. And that brings us to delineation techniques. Several devices are recommended based on the results of studies and field practice. Steady burn lights, vertical panels, and retroreflectors. But a word of warning, while these devices will enhance barrier visibility, they can become deadly projectiles upon vehicle impact. Or they can cut off body parts of passengers ejected from vehicles in a collision. The devices and mountings shown throughout this video were selected because they minimize this risk. Type C steady burn lights are low wattage battery powered lights with yellow lenses. They are mounted directly on the top surface of barriers. Steady burn lights work fine on tangent sections of barriers, and they're especially recommended for curves and transitions. They clearly outline the travel path well ahead of the vehicle, and they don't depend upon retroreflection from headlights for visibility. Vertical panels are another recommended form of delineation. These panels show direction and are retroreflective for good nighttime visibility. The standards require that the panels be 8 to 12 inches wide and a minimum of 24 inches high. Be sure that the panels are installed so that the stripes are angled downward in the direction that traffic is to pass. Like the steady burn lights, vertical panels are fine for delineating tangent sections. They may be supplemented with steady burn warning lights if used for channelization at night. This is especially the case where horizontal curves require good path definition. The decision to require the adding of warning lights should be based on an engineering study. Next up are retroreflectors. They include simple devices such as this small plate with retroreflective sheeting on it, to more sophisticated devices based on cube corner retroreflectance principles. As you see, these retroreflectors have a raised shape that's designed to reflect light better. Retroreflectors should be used only where there's a need to supplement standard channelizing and delineating devices. Now, so far, most of the channelizing and delineating devices you've seen in this video program have been positioned on or above the top surface of the barriers. But retroreflectors are sometimes side-mounted, positioned anywhere from just below the top of the barriers to all the way down at the base. The most popular position, however, seems to be from 5 to 16 inches down. Retroreflectors must conform with the color coding requirements, that is, yellow devices on the left side of the roadway and white devices on the right. Barrier end treatments and their delineation require special measures. The ends of barriers often pose a hazard to drivers. Good engineering practice requires that the danger be reduced by providing a crash-worthy end treatment. Details on appropriate treatments are discussed in the AASHTO Roadside Design Guide. A Type 3 object marker should be mounted at the approach end of the treatment. The marker should have approximately the same width as the treatment and should be mounted 1 foot above the ground. Drums or other proper channelizing devices should be used to channelize vehicles up to and past the barrier end segments to tie into the rest of the barrier installation. Where channelizing devices are used, the barrier end segments must not have any delineating devices placed on them. Delineating devices would only cause confusion. Where channelizing devices cannot be used due to space limitations, the end segments must be delineated. The MUTCD allows the use of yellow warning lights, but only the first 2 may be the Type A flashing kind. The rest of the lights must be Type C steady burning. Now, to point out some other delineation techniques and guidelines. In some states, top-mounted devices are supplemented with side-mounted ones on the same barriers, or they are alternated from barrier to barrier. The purpose is to increase nighttime visibility and to keep glare and dirt from making the devices ineffective. In some states, another delineation technique is to paint all the barrier segments with white pigment. The paint can be made more visible at night by adding glass beads. Other techniques call for painting only the approach segments, either all white or with diagonal orange and white stripes. Barriers can also be made more visible if white cement or white aggregates are used in their manufacture. Another factor in making devices effective is spacing. The spacing greatly influences how well motorists will see the devices and follow the path they define. Typically, on curves and tapers, you should space devices at an interval in feet that's equal to the speed limit in miles per hour. For example, for a 40-mile-per-hour speed limit, the devices should be spaced 40 feet apart. On tangents, the interval can be twice the speed limit. For example, at 40 miles an hour, the devices may be spaced 80 feet apart. A barrier on the outside of horizontal curves is more visible than a barrier on the inside. Here, for example, the barrier is easier to see because it's on the outside of the curve, and therefore the delineation is more visible. So when the barrier follows the inside of a curve, you should space the devices closer to increase their visibility. The rule is, the smaller the radius of the curve, the greater the need to reduce the spacing of devices. Many work zones have another problem: glare from the headlights of opposing traffic. Drivers have trouble seeing the delineation while looking toward the blinding lights. One solution to the problem is a glare screen. With retroreflective material attached at intervals to individual blades, the glare screen both blocks the opposing headlights and delineates the roadway. The maintenance of delineation and channelization devices is critical. Think of it in terms of 3 activities: routine maintenance, replacement due to damage, and cleaning. As part of routine maintenance, highway agencies should make frequent night reviews to determine the effectiveness of traffic control devices in work zones. Be sure to service the warning lights. Through time, their batteries become weak and their lamps burn out. You can replace lamps and batteries according to a schedule or on an as-needed basis, but always be sure to replace any burnt-out lights promptly to avoid gaps in the delineation or channelization. Routine maintenance also applies to devices that have lost their retroreflectivity because of constant exposure to the effects of heat, cold, wind, moisture, dust, de-icing chemicals, and vehicle emissions. You should replace such worn-out and faded devices when they no longer function properly. As for replacement due to damage, first, there's never a shortage of accidental damage. When devices are struck by construction equipment, traffic, or other objects. And there's intentional damage as well. Both the theft of devices and vandalism can take a serious toll, especially in high-density residential areas. The replacement of devices at such locations may become a regular task. The third maintenance activity is cleaning. Although it should be obvious that the devices and markings need to be cleaned frequently, field practice tends to neglect this duty. And that's a serious problem, because the same grime that eventually damages devices and markings causes more immediate problems by reducing their visibility. While all devices get dirty, studies show that dirt accumulation on channelization and delineation devices increases as the mounting height decreases. So side-mounted supplemental devices need more frequent cleaning than top-mounted ones. Nevertheless, you should routinely and thoroughly clean all devices to allow them to be seen by motorists. And while you're cleaning them, inspect them for damage and replace them as necessary. The selection of channelizing and delineating devices by government agencies and private contractors should be based on several key factors. If you're among the decision makers, you ought to first consider those devices that meet the national standards and their overall effectiveness. How well do they delineate barriers and define the path? Well, this is basically a function of how visible they are. And visibility is affected by a number of things, including size. The current MUTCD standard allows the use of devices with a minimum dimension of approximately 3 inches. But you should consider using devices with larger retroreflective areas, say 24 square inches as a minimum. Research shows that larger devices are more effective than smaller ones. More effective, yes, but not necessarily more cost-effective. And cost is a legitimate concern with all devices. Besides the variations in purchase price, there are variations in the costs of installation and maintenance. For example, These modular assemblies of glare blades are much easier and less costly to install than are the individual blades that must be anchored in place one at a time. However, the cost of modular assemblies is much greater than individual channelizing or delineating devices set at the appropriate spacing. Another example of cost consideration concerns Type C steady burn warning lights. While they receive high praise for their effectiveness, their higher installation and maintenance costs have stimulated greater interest in passive retroreflective devices. The maintenance factor in device selection is also evident in the issue of top-mounted versus side-mounted devices. There appears to be a strong preference for top-mounted devices because side-mounted ones require more servicing and are harder to get at. The side-mounted devices should be used only to supplement standard channelizing and delineating devices. Another maintenance point that might affect device selection concerns cube corner type devices. Compared to other devices, they lose less retroreflectance because of dirt accumulated through long-term exposure. And one final point about selecting devices and markings. In urban areas, portable barriers are often used to protect pedestrians. But because streetlights and other illumination help us to see the barrier segments, some city officials wrongly conclude that there's no need to improve their visibility with standard devices. However, the NUTCD requirements apply equally to urban as well as rural situations. Actually, urban conditions call for increased attention to adequate visibility and delineation. Deployments of short sections of barriers are common because of intersections, driveways, bus stops, and crosswalks. With so many shifting traffic patterns and narrow traffic lanes, drivers need all the path definition they can get, and pedestrians need to be protected. One thing is clear, there's certainly a variety of channelizing and delineating devices and placement methods in use around the country, a result both of past and ongoing research and of trial and error practice. In summary, we recommend that you follow all national and local standards in providing effective barrier delineation through work zones, that you select and use the types of devices that will provide the best delineation, that you employ proper techniques in placing devices, and that you inspect and maintain the devices to ensure continued service and safety. Clearly, highway construction and maintenance work are always with us, and portable concrete safety-shaped barriers are here to stay. Barriers do their job of protecting motorists, pedestrians, and workers. But to be visible in all conditions, they must be delineated with effective devices that are correctly installed and properly maintained. By delineating barriers effectively, we promote safe travel through our work zones along the well-defined path.